Okay, I guess welcome everybody. So I'm going to give a very last minute talk today. So if if there's complaints, well, uh, blame them on Dan. Um, so the sort of intended sort of audience for this talk is some people who have sort of basically not seen anything about quantum computers before. I take it, probably some people in this audience don't fall into that category. Um, but I'm going to sort of first give sort of like a very sort of like introductory sort of like motivational view, like why do we care about quantum computers and maybe what are the challenges? And then, I'm a mathematician, theoretician, so I can't, walk out of here without giving you some equations. So I'm going to give you sort of like, the very basics of what a quantum computer is and sort of like what the operations are that you have in quantum computing. Okay, so I guess maybe to start, just to sort of give you some sort of like perspective on who I am. So I'm a faculty member in CSC in math, and my research is basically what can you do with a quantum computer? So this is a quantum computer here. There's Joe Biden for scale. Um, now, okay, so there's a pretty kind of a big machine, but actually, sort of like everything that you're looking at here, which looks like the quantum computer, most of that apparatus is like kind of the control logic or the cooling, and the actual quantum chip is like something really tiny, right? So this is even though there's a huge sort of thing going on, the actual processor is tiny. And then, what does my research look? It looks nothing like that. It looks like stuff like this, right? Which is just, I'm a theoretician, so I work with at the sort of like this level. I'm not gonna sort of, you scare you too much with this kind of thing during the talk, but this is, sort of like, kinds of things that I think about. So, okay, so why do we care at all about quantum computing? I mean, like, there's like huge investments like all across the world. So there's like, these like major tech companies who are investing. There are some particular countries that are investing a lot in quantum computing. And there's even like sort of like a whole host of like quantum computing startups. So clearly like there's like something going on here. And what is going on? Well, it's because there's this like kind of promise with quantum computers that for certain problems, quantum computers can sort of be exponentially better than what we think a normal computer could do. So what are these problems? They're kind of surprisingly specific. So just before I sort of get into what quantum computers are good at, there's a lot of things that quantum computers are not good for. And so one of the things we have to do is sort of like hone in on exactly these sort of specific problems. But okay, so what are some examples? So the first one is almost like tautological. It seems like almost silly when you say it, which is that quantum computers are good at simulating quantum physics. So if you have some like small physical system and you want to sort of like probe its properties, a quantum computer is a good candidate for doing that on. It turns out that simulating these systems with like a normal classical computer, probably takes a long period of time. Whereas with a quantum computer, we can at least in principle simulate them very efficiently. So this is one sort of like maybe like sort of like physics, science sort of reason to study quantum computing. Another sort of like much more sort of like practical concern is that there's a efficient quantum algorithm for factoring numbers. So like if I had the number like 15, I can factor it to like 3 times 5. And okay, so why is this important? Well, basically like the whole world economy is like based on the fact that this problem is hard, right? So like encryption on the web, public key cryptography, a lot of it's based on this protocol called RSA, which is based on the intractability of factoring. So if we actually had, quantum computers, the full-fledged quantum computers today, when they could just, factor, sort of a lot of the sort of, basically immediately break a lot of the cryptography which is used online, which is sort of like, that's why like the NSA and lots of governments around the world are excited about quantum computing. And then maybe most speculatively, quantum computers can also be used to solve sort of like large systems of linear equations, but there are lots of caveats in there. I'm not going to get into the caveats there exactly, but like, there are some specific large linear systems where if the conditions are just right, you can use quantum computers to get a speed up. Okay, why is that important? Well, like all kinds of like machine learning problems are like exactly in this framework. So if you can find like just the right machine learning problem, then maybe a quantum machine learning algorithm might have some kind of exponential advantage over a classical one. Okay, so these are just like this is like yeah happy times, right? Like here are all the problems that these are all kind of important problems that quantum computers seem to be sort of like fundamentally better than classical computers for. I did want to mention, this is kind of something that a direction that I work a lot in, is that like here are all the things that we could do, but the quantum computers that we have today can't do these things. At least they can't do impressive versions of these things. The quantum computers that we have today are sort of like very small. So what is, I guess one way of saying this is like, quantum computing is like very much a nascent technology. So I like to sort of like compare these sort of like two pictures here. So these slides are a bit out of date, but this used to be like sort of like one of the state of the art quantum computers here, and this is like ENIAC is like one of the first electronic classical computers, and you can kind of see that like they're both these like huge sort of like unwieldy machines, sort of like taking up like most of the room. And I tend to think we're kind of in an analogous era right now with quantum computing, where these machines are they're powerful in some sense, but they're still sort of like extremely limited. So what's at least one reason that these machines are limited. So this is going to be sort of like my working picture of what a quantum computer is for the rest of the talk. So this is a quantum circuit. So it's comprised of sort of like these input gates. So it's like think of like you put in sort of like you can think of these inputs as being like states of an electron or something like this. So you have a quantum circuit which is acting on these various different quantum particles. And then you have these sort of like local operations that sort of manipulate these particles, sort of like in sort of like these pairwise interactions. And then sort of at the end, there needs to be some procedure for like taking something which looks kind of quantum and like reading out some kind of like classical measurement from it. Like you actually get like a sequence of bits that tells you, something interesting about your system. And sort of the problem with these sort of like quantum computers that we have today is that basically at every step in this process, there's some error. So like maybe you initially wanted to prepare some kind of electron, but you prepared it in a slightly different state that you thought it was, or you tried to apply some sort of like pairwise interaction between your electrons, but you ended up not quite applying the thing that you wanted. And in fact, even when you go to measure and you try to look at it, there could be error in the way that you look at it. So there's errors sort of essentially like all over the place, and sort of without this sort of primitive called quantum error correction, which requires a level of sort of like technical sophistication that we're not quite there yet with our sort of like current quantum computing experiments. We're actually kind of close, but in any case, without quantum error correction, what will happen is basically all of these errors will just like add up in your system. So like every time you go to do an operation, the error from the previous thing will just add into the new error. So like what this essentially means is like you can't actually have that total, like the total number of operations in your quantum circuit can't be that big, right? Because if they're too big, then eventually all these errors will sort of like add up, and then when you go to measure, like the error will just kind of like dwarf any kind of signal that you are getting from your quantum computation to begin with. So okay, so we can ask this sort of like a question, are these sort of like near-term quantum computers sort of better than their sort of like classical counterparts? And there's been like a variety of different sort of like things that have been proposed, from like chemistry to machine learning. And what I care a lot about is sort of like provable separations. Like, can we prove that these quantum computers, these like sort of models of near-term quantum computers, are doing better than classical computers? This is actually still kind of an open question. It's very hard to prove these things. So there's one sort of thread throughout my work is this sort of like quest for quantum advantage. Can you sort of like prove that a near-term quantum computer can solve a problem that can't be solved by classical computers? I wanted to sort of like point out like a very sort of like amusing instantiation of this sort of like whole picture. So some of you may be familiar with this like very sort of foundational, like it was amazing for its time. This is a foundational experiment done by the Google group, And so they ran this, somewhat large quantum circuit, and they basically said that like any classical device which was doing the same thing that the quantum device was doing, like if it was perfectly if it was simulating the what the quantum device was doing, then it would require basically a state-of-the-art supercomputer. Like imagine the biggest supercomputer on Earth, and then also give that supercomputer like 10,000 years. That's quite the claim. Okay, so that and then okay, so then their quantum experiment ran in sort of like 200 seconds, right? So okay, 200 seconds versus like 10,000 years, like okay, that's pretty significant difference. A quantum computer really looks like it's doing quite well. But then like I don't know, like 5 days later or something like this, the IBM team came out with a sort of proposal, and they said like, well, actually, I think if you were kind of when you made this like 10,000 year estimate, you were kind of doing something very stupid. Like you should have been using memory in a different way. And if you did memory if you use your memory in a different way, you could actually sort of bring down this simulation time sort of significantly. And it turns out people started like implementing and sort of like refining these ideas. So now we have like a classical sort of simulation method that runs in like something like 300 seconds. Okay? So we went from like 10,000 years to like 300 seconds. That's a pretty big change there. And so, it just kind of goes to show you that although there's a lot of promise with these sort of quantum systems, there's also some pitfalls, because classical algorithms actually can be quite clever and can sort of simulate a lot of the same things that the quantum thing is doing. Okay, and so I guess that's sort of like the takeaway. So the good news, as a sort of a high level picture, that quantum computers have sort of a lot of potential as sort of like this kind of fundamentally new computational platform. But sort of like the bad news is that sort of like the current quantum computers that we have, sort of they're not very good, and sort of like we need more investigations into sort of like what exactly they can do. So I mean, this bad news is actually sort of like a good news, right? For me, like this kind of why I have a job, right? It's because I spend time doing this kind of investigation. But it is somewhat of a reality check on sort of like subtlety of quantum computation and what needs to be done to sort of like understand it more and how it can be used. Okay, so that was my little sort of preface of like high level picture of quantum computing and sort of like some of the things I'm interested in. Now I'm sort of kind of like totally change gears and just sort of like try to give you the sort of like mathematical nuts and bolts of like what a quantum computer actually is. And I'm going to introduce it in like sort of a weird way, like in a way which is like I'm going to try to introduce it in a way which sort of like points to exactly sort of like where is the novelty in quantum computing? Like what is the new thing about quantum computing which is actually giving us our power? And I'm not sure I'm going to achieve my goal, but I will at least try to achieve my goal. Okay, so okay, here again is our picture of a generic quantum circuit with our inputs, our gates, and our measurement. Oh, by the way, I think this is maybe I should say this now, since this is going to be more of a like just like introduction kind of thing. Like please feel free to stop me if there's something I'm saying up here that doesn't make any sense or you want further sort of clarification on. Because I have no agenda here or things I want to get to. So I don't even have that many slides in total, right? So if you don't ask questions, maybe this will be a very short talk. But okay, so here's our generic picture, and I want to sort of like focus in on sort of like say, okay, what exactly is one of these quantum gates, anyways? Okay, so I'm going to sort of try to draw an analogy between sort of quantum circuits on one hand and classical circuits on the other hand. Okay, so I am going to sort of like assume that you have like a little bit of knowledge of like what a classical circuit is, but hopefully it will become clear as I go on. So this is a depiction of a classical AND gate. So okay, so here's my sort of like first attempt to sort of like say like what is fundamentally different about a quantum computer than a classical computer? Well, the first thing that you might think of a law of quantum mechanics is that physics is inherently reversible at the sort of like quantum mechanical level. So what does that mean? Like quantum mechanically, it means that like if I like drop an egg and it like shatters into a million pieces, there's no law of nature that says I can't just reverse that process and get the egg back, right? Like at the particle level, like no information is lost, right? But typically when we think of computing, we think of losing information all the time, right? So if we think of this, this AND gate, which is like one of the fundamental building blocks of a classical computer. Like if I have a 1 as my output, right, then I know like both of the inputs must have also been 1, right? Because like the only way that the output of this is 1 is if both of these are 1, right? But if the output is 0, right, then it might be the case that both the inputs are 0, both of the inputs, well, one of the inputs is 1, the other one is 0, and so on and so forth. So I've lost information in my classical circuit. And maybe there's some sense in which like the reversibility of quantum circuits is something which is sort of like fundamentally powerful and useful for computation. But it turns out that's not the case, right? So it turns out that like basically every classical circuit can be made reversible with like without too much trouble. So you can, even though like our computers are constantly doing irreversible computation, it turns out we could actually do it all reversibly and it would just be fine. So here's one example of a reversible classical gate, which is very important. So this is called the sort of controlled NOT gate. And basically what it means is like, you can think of these as the first input, second input, and you sort of like flip the second input if the first input is 1. So like here's some example, right? So the first input is 1 here, and the second input is 0. So because this is 1, you flip the 0. Here's another example. Because the first input is 0, you don't do anything the second. So this is it's not too hard to convince yourself that this gate is reversible. So if you know what the outputs are, you can immediately determine what the inputs were by running the exact same circuit over again. Okay, so it's not reversibility. So something else that you might know about quantum mechanics is that it's sort of like inherently probabilistic, right? There's like randomness which is going on sort of very fundamentally in a quantum circuit, where we typically think of our sort of computers, our laptops, or whatever, as not being random. Like they follow sort of like a deterministic set of rules. So maybe somehow this randomness is the thing that's giving us the power. I claim that it's still sort of like that doesn't really change much, right? So I can also have randomness and I can throw it into a classical circuit. So instead of having inputs that look like 0 and 1, say, I could have a probability distribution over inputs, right? So with some probability it's 0, and some other probability it's 1, right? So how might I go about sort of like representing that? Well, I'm gonna choose to represent it in kind of a weird way at first, but this will make more sense later. So I'm going to represent all of the probabilities as sort of like a vector. So we can see here, like, so basically it's saying like the probability that I start in the state where both of the inputs are 0 is like 20%. The probability I start in the state where the first input is 0, the second input 1 is 30%, and so on and so forth, right? So I can define some kind of probability distribution over my input values. And then, well, what is my gate doing? My gate is basically just sort of like permuting this probability vector, right? So let's like go through like some examples, right? So like suppose my input was 0, 0, I see 0, 0 with 20%. So then after I've applied my gate, then I still see 0, 0 with 20% because that's what the initial probability was. If my input was 0, 1, I see that with 30%, which means I also see 0, 1 with 30% in the output. Now, if my input was 1, 0, I see that with 40%, but then I get 1, 1. So now I see 40% 1, 1 at the end. And so, and similarly, if my input was 1, 1, then I see 1, 0 at the end. So I see that with 10% probability. So sort of, we can sort of represent the classical circuit as basically just an operation which sort of changes around the probabilities in a vector. In fact, there's a very sort of general way of stating this. I can think of a classical circuit as just a big matrix where you multiply this matrix by this probability vector that in your input, and you get the probability vector for the output. And the condition that you need is that if the initial probability sum to 1, then the probabilities afterwards sum to 1, right? That just that's sort of like preserving our intuition with like, all events happen with 100% probability, right? Like sort of the probabilities sort of split up the space. So, right, so I can sort of completely capture what's done by in classical circuit by I have this input vector describing the probabilities, and I have this operation, this matrix A, which is, in this case, this matrix A is sort of captured by this C0 gate. And then I have some output vector. I would just multiply the matrix by the vector, or multiply the vector by the matrix, And I just need that the sort of like the sum of the vector entries before equal to the sum of the vector entries afterward. Okay, this is kind of like a crazy way of describing classical computation. You know, in you're like, this is probably not how you all learned about classical computation originally, but I claim that it plays very nice with the quantum way of describing things, because the quantum way of describing things is exactly the same, except for now instead of having probabilities over these values, you have these things called amplitudes. Okay, so what is an amplitude? It's like kind of like a generalization of a probability, but instead of the probabilities sort of like strictly being like these sort of like positive percentages, they can be sort of like stranger things with like real numbers with like positive and negative signs. But the key property of a quantum circuit is that when you have the amplitudes, instead of applying a matrix that preserves the sum of the entries, now you're applying a matrix which preserves the sum of the squares of the entries. Okay, this is like a kind of like should be sort of like, if you haven't seen this before, this should be kind of amazing, right? Basically, all of quantum mechanics, everything that's different about quantum mechanics, that's in terms of computation, how it's different from classical mechanics, can be broken down to this one simple fact that quantum operations preserve the sum of the squares of the entries of your amplitude vector, and classical computation just preserves the sum. It's like the sum versus the sum of the squares. Everything can be boiled down to that. It's very surprising if you haven't seen it before. But this is essentially where all of the weirdness in quantum mechanics comes from. And one of the ways in which this sort of manifests, and we'll see some examples later, is that when you're preserving the sum of the squares, like your amplitudes no longer need to be things that look like probabilities. Like you could still kind of squint and think of these as probabilities, but if I put like a minus sign here instead, you would like, there's no sense in which that makes sense classically, right? To have some minus of a probability, but quantumly having a negative amplitude is just totally normal, right? Because when you square it, you will get something positive. So when you sum up the squares, you'll still get something that adds up to 1. Okay, so I've sort of described what it means to apply an operation to a classical and quantum state. Now, what does it mean to sort of extract the sort of I want to like look at if I were to scroll back sort of my first picture where there's like this part where you're sort of like actually looking at the quantum state to extract some classical bit string. So what does that look like? So once again, we're going to sort of like draw on our classical analogy. So imagine I have a coin, I flip it, and while it's in the air, like, let's say I flipped it perfectly while it's in the air, I can sort of describe the state of what it's going to be like when it lands as like, well, with 50% probability, it will be 0, and with 50% probability, it'll be 1 if I've like flipped it perfectly fairly, right? And then when it lands, I can look at it and I can see, well, did it land on like heads or tails? Did it land on 0 or 1? And so once it lands, I know exactly like, oh, like it landed in the 0 state, so I can describe it with this vector where it's like, now it's 100% probability that it's in the 0 state because I'm just looking at it there in the 0 state. So quantumly, we have sort of like basically the exact same thing that happens. If I have this like vector of amplitudes, now I want to actually sort of like look and see what my state is. What is the state of my system? Is it 0, 0? Is it 0, 1? Is it 1, 0? What state is it? So this this is like a poor depiction of what this might look like in a lab. Like you have some electron, you like shine some laser at it to sort of like extract and see how it bounces off to extract some information from it, and the sort of map that you get, the probability with which you see a particular item is related once again to the square of the amplitude. So if I were to have this state here and I were to sort of look at the state, then I would see the state 0, 0 with probability 2, 0, 1 with probability 30%, 1, 0 with probably 40%, and 1, 1 with probability 10%, which is just sum of the squares of these guys, or just the squares of these guys, rather. And this is why it's important to preserve sort of like the sum of the squares of the amplitudes, because like once again at the end when I look at it, now I have a probability distribution. So this should make sense in terms of our classical intuition of like, if I sum up all of the possible events, that needs to add up to 100%, right? And so that's why the sum of the squares of these things needs to add up to 100. Needs to add up to 1 rather. But then, okay, once I do sort of, see a particular outcome, then once again, it's like the coin lands, is the sort of the direct analogy. With 40% probability, I see it in 1, 0, but then once I actually observe the 1, 0, then the whole state collapses. And now you just see 1, 0. So you may have heard of this sort of principle that when you measure a quantum state, you're sort of like fundamentally destroying all the quantum information inside the state. And this is what's going on, right? You had this sort of like nice vector of amplitudes before, some carefully constructed thing, and then you go to look at it, and like then it sort of collapses all down to like a, you know, that piece of classical information. So this gives you a little bit of intuition on why actually building a quantum computer is hard. It's not so easy to maybe kind of have to take my word for it, but like basically you can think of noise in a quantum system, at least one component of noise in a quantum system, as being like the outside world is trying to like look at your system, right? Like electrons are like coming in from everywhere, like neutrinos from the sky or whatever. They're coming in and they're trying to look at your quantum system, right? And you know, what exactly does it mean to look at it? It means you're sort of like carrying away some quantum information. So basically the outside world is trying to like collapse you down into these states, which are not very interesting, right? Like classically we saw the same kind of states, but and really to do interesting computation, we need these like very intricate sort of amplitude patterns. Okay, I've already emphasized this. So yeah, so the sums of the squares must be 1. So I've also mentioned this, so now they can be negative. And I think one for those of you who have physics background, this will maybe be useful, is that sort of quantum states are sort of like, you can think of them like kind of like waves, where sort of like the positive amplitude corresponds to like a crest in a wave, and the negative amplitude sort of corresponds to sort of a trough in the wave. And so like, you know, basically what you're trying to do is you're trying to find interesting sort of interference patterns where these things sort of like cancel out. So on the outcomes where you don't care, these sort of like waves and troughs sort of like cancel each other out. And on the outcomes that you do eventually want to see, you want these waves to sort of like coincide with each other. Now that seems like very magical, like when it's like phrased in that language. But I claim it's like once you start sort of like working with the sort of like the fundamental gates in the system, it's less magical than that, but it still sort of looks like this. So I guess, yeah, so the sort of like analogy here is sort of like you may have seen this like a double slit experiment before. You know, kind of what's going on there is exactly this quantum mechanical interference of waves. Okay, so let me give you sort of like one small example. So this is an example of a quantum state. So it's 1 over square root of 2, 1 over square root of 2. So just like two states, 0 and 1. And if I were to look at the state initially, then what would I see? Well, I would see this with 50% probability and this with 50% probability, right? So that's kind of like a random coin, right? But I even put it on the slide. Now imagine I apply a quantum operation to this quantum state here. Okay, so this is the well-known sort of Hadamard transformation if you've seen it before. But okay, so what is actually going to happen? Okay, so we take this row and multiply it by this column. We're doing matrix vector multiplication here. So we get 1 over square root of 2 times 1 over square root of 2, which is a half, plus 1 over square root of 2 times 1 over square root of 2 is another half. So we get 1/2 plus 1/2.
All right.
But down here we get 1 over square root of 2 times 1 over square root of 2 minus 1 over square root of 2. So we get a half minus half. So this is sort of like the quantum interference, but then now you can kind of see it in the math. This is what's happening here. These two amplitudes are kind of like canceling each other out. And now what you get afterwards is a state where you just have basically all of your amplitude on the first state and none of the amplitude on the second state. So this is kind of amazing, right? Because you initially took a state which was sort of like 50-50%, and you applied this quantum operation to it, a reversible quantum operation to it, and you got a state which was 100% probability it was in the 0 state. Now, maybe this is not obvious to you, but this exact kind of transformation is not possible with a classical reversible circuit. Just totally impossible to have this kind of information. If I have a state which is completely scrambled, like 50%, 50%, any reversible way that I could try to manipulate that would leave me in the 50% state. But sort of quantum mechanically, because I have this sort of ability to sort of like cancel out amplitudes, somehow I'm able to sort of like sort of escape from that box in some sense. Okay, so I think this is my final slide. So what actually is it that makes quantum computers more powerful than their sort of classical counterparts? So I think the high level intuition is kind of what we've been talking about, that these amplitudes allow you for these like intricate interference patterns that if you're very careful can sort of allow you to do certain kinds of algorithms that you wouldn't be able to use before. This is a sort of a possibly sort of a more revealing way of thinking about things, but also requires some more background knowledge, which is that you can think of quantum computers. One of the advantages they have is they can sort of efficiently perform certain change of basis operations. So like if you've seen the Fourier transform before, quantum computers can sort of efficiently implement the Fourier transform. And then sort of like the final thing I will say is that classically, randomness typically only tends to help us in sort of very limited ways, and we often don't need to have access to sort of like the full sort of probability vector in the same sense in which quantumly we usually do. Like you often do need to know sort of like the full amplitude vector in order to do useful calculations. And so just to give you sort of like some intuition for why that's scary, right? Is because, well, if I have 2 qubits here, then I have to keep track of these sort of like 4 amplitude parameters in order to know what's going on in my system. But of course, if I have an n qubit system, then the number of amplitudes that I need to write down is 2 to the n. It's exponentially many complex numbers that I need to write down in order to describe the state of my system, right? So if I need exponentially many parameters in order to describe my system and what it's doing, then that seems very powerful, right? Because it's not exactly this, right? But there's some sense in which you're taking like an exponential amount of information and you're sort of like compressing it down into sort of like a polynomial amount of information. Now it turns out that argument is not rigorous. It's not quite. It's a lot more subtle than that. But nevertheless, it seems like, for the most part, if you want to classically simulate a quantum system, you actually need to have all these 2 to the n amplitudes in practice. So that sort of exponentiality seems kind of inherent. And whenever that exponentiality is kind of inherent in general, you hope that for very specific problems, like the ones we talked about at the very beginning of this talk, those also sort of will require sort of an exponential amount of work to simulate. And if they require an exponential amount of work to simulate, then the quantum computer is doing something sort of like very fundamentally more powerful than what the classical computer is doing. Okay, so that's all I have. I'm happy to take questions. I'm happy to get out of here, whatever you guys want. Yeah.
Yep, n bits, then that gives us 2 to the n options. How is that different from n qubits giving us 2 to the n amplitude?
That it's no different, in fact. It just turns out that quantum mechanically, it's sort of easy to describe with a polynomial size circuit. It's easy to describe or generate amplitude vectors that seem to require exponential amount of number of parameters to describe classically in this way. Whereas classically, this doesn't sort of it's harder to, like, it's almost like tautological. If I have a simple classical distribution and I manipulate it with a short classical circuit, then that distribution is going to be easy to describe classically, whereas this one is not. But you're like, fundamentally you're right, and this is in fact one of the reasons I go into this like whole long spiel about all of the similarities between quantum and classical, because many people will just tell you this part, and they won't tell you the thing that you said, which is like, actually that's also true classically. So there has to be n something else, and the n something else for quantum computers is really the fact that you have these amplitudes rather than probabilities. Yeah.
So broad strokes, what are the major steps between everything you've shown here and everything that you do?
Good question. So what I tend to do is I tend to look at very sort of restricted models of quantum computers. So instead of like, so this is like, this is kind of like the generic setup for what a quantum circuit is, but you could try to model what a near-term quantum computer is doing by sort of restricting the kinds of quantum circuits that you deal with. So, a particular kind of quantum circuit that I deal with all the time is a class of quantum circuits called shallow quantum circuits or constant depth quantum circuits, which just means like you can't apply that many layers of gates, right? Like you have to sort of only apply a few layer of gates. And the idea behind that is like it models a scenario in which it's like your computer, you don't have that much time to run your quantum computer because like eventually it's just going to sort of like the error in the machine will sort of accumulate too much if you apply too many layers of operations. But then it's sort of, then you have the sort of like mathematical abstraction of that, which is like, okay, now let me just sort of capture that sort of idea of decoherence into like a shallow depth quantum circuit. And then you can sort of say like, what are the power of these kinds of quantum circuits, and can they sort of like outperform what shallow classical circuits you do, for example. And so that involves like a lot of like complexity theory. So if you've taken a complexity theory class before, that's just one example. I mean, the short answer is like there's a lot of like math, but I work on a lot of disparate kinds of things within quantum computation, but typically it involves like combining sort of what I've shown you with classical complexity techniques to try to make a meaningful comparison between what a quantum computer is doing and a classical computer is doing. Yeah, I believe there was a question behind. Yeah.
So I'm a bit unclear on quantum gates specifically. So the way I understood is quantum gates have like some like operation that they can do on their inputs to give a set of outputs. But like, how does that like, I don't know, look like, at least in comparison to classical gates? Because classical gates would be like, I mean, think even just as simple as the AND gate, right? You would have two inputs that would just output one if both of them are one. How would that look like, I guess, even in a quantum circuit? Especially if you don't know the inputs. The inputs are like these amplitude probabilities. How would you even make an AND gate there?
So in the same way in which I took this classical C0 gate, and I didn't write it on the slide, but I can convert it into a matrix, and then like I can convert what this thing is doing as a matrix, and then the way that the classical circuit evolves is basically like taking this probability vector and multiplying it by that matrix. I'm just talking about something classical now. The same thing happens quantumly, right? Like you can take a quantum gate and represent it as a matrix. And then how the state evolves is you take the state and you multiply it by that matrix.
Yeah. Yeah, I mean, I guess, yeah, but like, I don't know, it feels a bit strange because if the inputs are like random, then how can you doesn't that mean that like every quantum gate has to be like handmade into like hard coded, I guess, because
Well, I mean, okay, maybe I'm not fully appreciating the question, but like although like you could think of it this way. You can think of like the input as being random, but the gate itself is being fixed. Like think back again to what this example was showing you, right? I was able giving like this is a deterministic operation here, right? Like you give it a 0 and a 1 and it spits out something, right? But now when I give it a probability distribution, it just sort of like acts on each individual element of that probability distribution simultaneously, right? Like with 20% probability, I was seeing the 0, and so now at the end with 20% probability, I see 0, 0, right? So like the exact same phenomenon can be like will be true for quantum circuits. Like I can break down what the quantum circuit is doing by first considering what it does to 0, 0, and then considering what it does to 0, 1, and then considering what it does to 1, 0, and 1, 1, and sort of adding up all of those possibilities together. And when you add it, you sort of like weight by the amplitude that you initially saw them. Like I get okay, so the one answer is that it's possible that it shouldn't be intuitive to you because quantum circuits are kind of weird. But if this is intuitive to you, then I claim that this should also be intuitive to you.
Yeah, like I get it from a mathematical perspective. It's just more like, how can you extract useful information from this, you know? That's a bit more confusing to me.
Oh, why you can leverage any of this to do useful computation is like extremely subtle question, right? Like why any of this is at all useful for computation is very you know, you have to really there's a lot of steps that you have to go through before you can understand why something like this is useful. You know, at the very intuitive level, it has something to do with the fact that you're allowed to sort of like if we go to our sort of like Hadamard example again, well, maybe this was a bad idea. It has to do with the fact that you have these sort of like interference patterns, like this kind of behavior you'll never see in a classical circuit, right? So somehow you need to sort of like leverage, you know, leverage this behavior when you're doing a quantum computation. And so like if you've seen things like the Fourier transform or something before, that will start to give you a sort of intuition for why this is actually useful as a computation technique. But I think it's a lot of people have tried and failed to have intuitive reasons for why quantum computers are powerful, right? It's not so easy to describe, which is why I sort of just prefer to sort of just like give you the math and say like, okay, now now what can you do with this math? Yeah.
Yeah, so sorry if you may have already said this, but you mentioned that when you're doing quantum computations, you get errors through while you're in between. So I was just wondering how, like where do these errors come from? Or like why do we get errors?
Yeah, great question. So the first answer is that it very much depends on exactly how you're implementing your quantum computer. So quantum computing is kind of actually a sort of interesting stage in development right now. Like you know, for classical computing, it's like we've almost like solved classical computing, right? It's like you build it in silicon, and then like we have like very good ways of building transistors and things like this. Quantum computers, not the case, right? Like everyone has like tried every different kind of way of building a quantum computer that has fundamentally different substrate at the base level, and so the errors in different quantum computing platforms, like different instantiations of quantum computing platforms will come from very different places. So like for instance, one way to instantiate a quantum computer is actually in like the sort of like phases of light. Like you're actually shooting like photons at mirrors and they're like bouncing around and interacting with each other. And in that model, one of the biggest areas of error is like basically your photon like bounces out of the system, right? Like you actually just lose the photon. There are other there are other systems where you basically have like a bunch of ions which are like sort of like trapped in these sort of like magnetic wells, and in that paradigm, the dominant or one of the dominant forms of error is sort of like crosstalk between the like adjacent ions. Like if one ion moves in a certain way, that it has a force that affects the ion which is next to it. So I don't know if that's a great answer, but it comes from a ton of different places. Some of them for kind of very sort of like fundamental reasons, like in terms of like physics and like things from the environment interfering with your system. A lot of times it's just like stupid machine error. Like you built the machine to do a particular thing, but like it doesn't quite do the thing that you want it to do. And like one of the things about quantum mechanics which makes it so difficult is errors are continuous, right? Like if you think classically, like if I just have a 0, 1, there's like not that many ways I can corrupt a 0, 1. Right? Like I can flip the bit, can lose the bit, I can erase the bit. Like I probably just like enumerated all the things that you can do to a bit, right? But sort of like with a qubit, with a quantum version of this, like these amplitudes are continuous, right? So I can like rotate the qubit in any different way, and sort of whatever you're doing to sort of like mitigate that effect kind of has to be sensitive to all of these possible rotations that you could have. And that makes it a lot more difficult as well. Like there's some sense in which classical computers kind of have like a built-in error correction mechanism to them just because of this fact. Like, imagine for instance that like this is a very simplistic model, right? But like imagine I measured a bit, whereas like I had a low voltage or a high voltage, right? Like low voltage meant 0, high voltage means 1, right? And then there's some threshold cutoff between like what one means and what the other one means. If there's like a little bit of voltage difference at in what I interpret as a 1, that doesn't really matter, right? Because I'm still like above that threshold. Whereas quantum mechanically, that won't be true. That'll actually, like if there's a difference in my state, that will correspond to sort of like a fundamentally different quantum state. Now that sounds really bad when I phrase it like that. There are ways of dealing with the error, but you have to be more careful. Yeah. You got to do both. So so error correction, generally the way that it works is you only start to see the error corrective properties once your hardware is already good enough, like the error level is below some threshold. So you may see this sometime if you like look around, you'll see these things called threshold theorems. And basically what a threshold theorem is saying like you have a specific way of doing error correction, and if your base level of error is below the threshold, then the error correction will make the error go down even further. But if your base level of error is above the threshold, then in fact these codes will increase the error. So this has like been a running joke in the quantum computing community for some time, which is that like all known or all implemented quantum error correction schemes are actually error increasing schemes because they're not below the threshold. Yeah.
Do you have a question from the Zoom meeting? How's the hardware of a quantum computer different from a classical computer? Is it mainly silicon or some other material?
So you can implement, we're really getting outside my area of expertise now. You can implement some kinds of things in silicon, but also you can, I would say the main substrate is currently not silicon. Like you can implement quantum computers in sort of all kinds of substrates. Yeah, that.
Is there any sort of thought on like using both classical and quantum computers at the same time, possibly as a way to mitigate the error?
In fact, that is exactly how it's done. So normally, if I can give you kind of a caricature picture of how quantum error correction works, what you do. So I mentioned all these sort of like continuous errors in quantum systems, right? So how quantum error correction actually works is you build your quantum system, like you can picture like imagine the entire space of possible states, quantum states that you could have. You imagine that big space. Quantum error correction is essentially you only want to work on states that live in a subspace of that state. So like there's a big space of possible states, and then there's like a small subspace where you actually want to work in. And then the way that quantum error correction works is, as errors happen in your system, you sort of start to come out of the subspace in some sense. And then how quantum error correction works is you actually sort of like project back onto that subspace. Now, when you project back onto that subspace, what's going to happen is like these continuous errors that I was mentioning before now become discrete, right? But I could have, if I had a continuous error in some sense, I could have, when I projected back on the subspace, I could have projected back into my original state, which is great, or I could have sort of like made a huge mistake, and now I've sort of projected in a way where there's like a very identifiable sort of signature that there's a mistake. And then you basically take all the signatures of the mistake, and if you've developed your quantum, if the rate of error is low enough and you've developed your quantum error correcting sort of system well enough, you'll be able to take, this is called the syndromes, you'll be able to take the syndromes, perform some kind of like classical computation on these syndrome bits, and then sort of by that classical computation, you'll have figured out what the error actually was, and then you will sort of like manually rotate yourself back into the thing that you actually want it to be in. So if you project it onto a bad state, basically you can detect what it is classically and then rotate back. So yes.
So in your research, you don't necessarily interact with quantum computers. You're more the theory behind the usability of quantum computers?
Yeah, I don't know if I've ever seen a quantum computer, to be honest with you. I've seen like very small sort of like prototypes. But yeah, I work very much in the math. I have worked with some quantum computing like startups and stuff, like doing theory work for them, but I'm very far from like ever touching hardware. Yeah.
Does quantum complexity theory vary with different hardwares, or is all of the theory pretty much the same?
That's a great question. So if the kind of theory that I like to do is agnostic to the hardware, but that's a bit of a, you sometimes kind of have to be a little bit aware of what the hardware is doing. So okay, so I did kind of lie earlier. I kind of like presented this as like sort of like the full picture of what quantum mechanics is, and basically, for the most part, this is the full picture. It turns out that for different kinds of systems, there's a different kind of structure to the what's known as the Hilbert space. Is the space of all quantum states that you can have. So for instance, if I'm working with superconducting qubits, particular kind of qubits, it looks like this. If I'm working with sort of photonic quantum computers, which I was mentioning earlier, it's a different Hilbert space, and your theory has to be different for that Hilbert space. So in fact, I have worked on photonic quantum computers before, and you have to sort of in that case, your theory does, it has to change. Now, I try to sort of like shy away from kinds of theory where you're like very, specifically looking at like, I have this particular interaction graph amongst qubits in my circuit, and I want to know sort of like what kinds of things I can do and what kind of depth, like something which is like very, very specific to the hardware. I try to avoid, but there are these sort of like big sort of like, physics differences between different kinds of platforms where your theory like you can't avoid having theory which is specific to those areas. Yeah.
This might be another out of your element. The progression of the physical hardware and the progression of the theory, are they intertwined with each other where one goes forward, the other comes with it? Is one really far ahead of the other one? Are they completely independent from each other?
Okay, so this is another great question. And I think maybe you'll get different answers depending on who you talk to. So historically, the theory has been way far ahead of the hardware. Like, we had theory of quantum computers in like the 80s, right? So like quantum mechanics itself in like the 20s, right? So like the theory has been there for a really long time, and kind of only recently within the last 5, 6, 7 years have we gotten like quantum computers that start to actually look like a useful device. And I would say for the most part, there's been a really fruitful collaboration between the theory people and the hardware people in terms of what are the interesting problems to run on these devices. I'm actually personally a little bit scared that the hardware people are going to catch up and they're going to say like, look, we have a 100-qubit quantum computer. You told us that was impressive. Now what can we do with it? And we're going to say like, actually, we have no idea what to do with it. Give me 1,000 qubits and then come back and talk to me. Like, I'm a little bit worried that we're gonna be in that scenario soon. They don't have they don't have 100-qubit quantum computers yet, at least like 100 logical qubits is what I really mean. So we haven't quite gotten there. But I think there is a real reckoning in the community right now of like saying like these quantum systems are really they're coming, and we sort of need to be like we as theoreticians we need to be ready for them in terms of what we can do. And I think it's a big open question right now. At the very least, sort of what can we do with these sort of like smaller scale quantum systems, like 102 qubits or 100 to 200, 300, like that number of qubits. Like what are the useful things we can actually do with them? It's actually not trivial, even to say anything useful about that setting. Yeah.
Could be physical simulation.
Yeah.
General purpose, or are they very specifically good at certain?
Yeah, specifically good at certain things. So I don't know if you know what a Hamiltonian is, but they're like basically there's these. You can think of them as like not graph theory Hamiltonian. He was a very prolific person. You can describe sort of like what the state of a system is by Hamiltonian, which means basically like a Hamiltonian, like it's a matrix. It's so known as a Hermitian matrix, and you can diagonalize the matrix. Okay, I'm really starting like I'm really using a lot of linear algebra here, but if you can diagonalize the matrix, and basically this will give you and sort of order the eigenvalues by how large they are, and this will basically give you energy levels. And sort of one of the sort of like fundamental sort of properties of physics is that like things in the world like to be at lower energy levels. Like they'll tend to like if there's a certain Hamiltonian which is governing a system, it will decay towards its base energy level. But this kind of comes with like a sort of a caveat, which is that there's some sense in which some energy levels are easy to find and some are not. So this almost looks like an optimization problem where like if you look at sort of the energy landscape of a system and it's very sort of like it's like always goes down or whatever, then you're likely to see your system is going to be in that ground state energy level. But if your energy level is what's known as a plateau, right? So like if you kind of look locally around you, it looks flat, but there happen to be these weird regions where the energy level goes down. If you take one of these systems and you look at it in nature, you'll probably tend to find it in the plateau system, right? Where because it's sort of like trying to find the low energy state, but like it's just too hard to find. Whereas like quantum mechanically, you can sort of like probe these low energy states sort of more directly. You can try to find them more directly, and you can hope that by finding them, you find some sort of more exotic states of matter that might be useful for things. I have actually no idea what people are hoping to find, but that's like the kind of basic idea. And that's the kind of thing, if your Hamiltonian is of a specific form, that's the kind of thing a quantum computer can do quickly.
Would be used for different purposes?
Yeah, that's a great question. There are certain kinds of tasks which are more like, and specifically some of these photonic systems have there's like in the background there's like some kind of sampling problem which is going on, like some kind of like graphs. The short answer is yes. There's certain kinds of problems that you can define for photonic systems. Like one is like sampling dense graphs from a larger graph. There's some sense in which there's a problem there which is native for a photonic system, which would not be native for a superconducting system. But I think if you talk to most people today, they're less interested in that kind of transformation or those kind of native operations, and and they're basically all trying to get to just a general purpose quantum computer, which is like described in the way that I like, you just hand it any gate and it'll tell you like how to, what the pulse sequences are in order to affect that gate on their hardware. Now, I don't think it's unreasonable to think that we will eventually see something like you suggest, where certain platforms are better at certain kinds of things than others. Like there will be certain gates which are native to a particular hardware platform, with just by virtue of what kinds of errors there are, it will be better to run it on that platform rather than another platform where you could, in principle, simulate that gate, but you'd have to do a lot more work in order to do it, and that makes that overhead would be sort of like too much. I don't really. It's a good question. I don't know what sort of the practitioners of the field would say exactly as to whether or not we have a good sense of what those will be going forward. But it wouldn't surprise me to learn that something like that is true.
It's 6. We only have the room till 6:30. So
I'm happy to leave.
put that up there. Put that out there.
Does anyone have any lasting questions?
So there's a bit of a joke also in the quantum community that everything's just about 10 years out or 40 years out. There's some particular number. Do you believe that there is a real target to getting out of NISC? Or do you, as someone who's been in it long enough, sort of see through that and sort of feel it's longer than anyone can really anticipate?
How old do you think I am?
I don't know.
No, I'm just joking. It's a good question. Okay, so what I'll say is, I don't like to make a concrete prediction. Like I try to like weasel out of it as much as possible. But if you take a graph and you look at 2-qubit gate fidelities over time. So what does that mean? That means like 2-qubit gate fidelities so fidelity is a measure of how well so you're trying to apply a gate. Fidelity is a measure of how well you actually applied that gate. So if your fidelity is high, it means you applied the quantum operation that you intended to apply. If your fidelity is low, you maybe applied something which is kind of close to what you intended to apply, but there's a lot of error, right? So if you look at the fidelity of 2-qubit gates over time, it goes like exponentially down. Like the fidelities get really, really close, or up. Sorry, error goes down, fidelity goes up. Right? It goes the fidelities over time are getting better and better and better, and we know there are theorems. Okay, the theorems do make some assumptions, but there are theorems which say like once you get to a low enough 2-qubit error, then you can apply, going back to this threshold theorem that I was talking before. Then you can apply quantum error correction, and once you apply quantum error correction, then you're really in business, right? Like then that really sort of like opens up a lot of avenues for you. So this is not the end of the story, right? Like because you can perform one 2-qubit gate really, really well doesn't mean that I can then immediately scale that up to a system of 1,000 qubits and still have that same fidelity over 1,000 qubits. The march of progress as it is, though, I just have a hard time seeing that it's going to stop. And like we're probably going to keep seeing obstacles, right? But we kind of know from a theoretical standpoint, if we just keep steadily making progress, we will eventually have to get to a point where it will turn into a quantum computer. Unless there's some real fundamental barrier to why quantum computers will work. Like some people, not me, but some people have proposed like crazy error models such that if that error model is true, quantum computing would be sort of impossible. But basically right now we have like no reason to think that any of those things are true, right? Right now, like most of the times, like things kind of go with our expectations. And so like, to put a concrete number on it, I think it would be totally plausible within the next 10 years if we had like 1,000 qubit, or maybe that's a little bit optimistic. I'll say 100 qubits, 100 logical qubits that we could sort of manipulate. Yeah.
Are there ways to like compute or calculate like these amplitudes before actually running like a quantum process, or do you have to run like a series of processes and then like use that data to like write down your amplitudes?
in fact, you don't want it to be the case. Like if it was possible to compute the amplitudes before running the quantum computer, then you don't need the quantum computer. Right? So the answer is like, we hope the answer is no, that there is no way, right? If the answer is yes, then every quantum computation can be simulated by a classical computation, which is just to point out, that is actually a possibility, right? Theoretically, we don't know that these two paradigms are different. Like almost everyone thinks that, there are some people who don't, right? But almost everybody thinks that these quantum computing is different from classical computing, but we don't have a proof. So something to keep in mind.
I think we can kind of finalize everything over here. If anyone has any lasting questions about anything at all, then you can go ahead. We can finish it there. Thank you so much.